So you've been looking at a simulation of the Milky Way and Andromeda colliding. It took only about 6 minutes for this whole simulation to play, but of course it occurred over the next 10 billion years or so. We will have a major collision with Andromeda in about 4 or 5 billion years. You know, we'll pass through, and then we'll kind of slosh around and eventually settle down to become probably a proto-elliptical galaxy, as we use up all the gas to build new stars, and we essentially stop building stars in about 10 billion years from now, or say 15 billion years from now, and then that's it. Red and dead galaxy. All right, so logistics. Problem set number 8 is on B-Space as of last night. It's due next Wednesday. I also posted the extra credit project details, which will be due in the first week of May, the first Thursday in May. I encourage you to take a look at that. I'll go over some of the details of that, say, next week, and you guys can ask questions about what you might be thinking in terms of projects. So the summary of that one sheet is that we would like you to sort of build a proto-research project. So something that's interested you in class. Many of you come to my office hours and ask interesting questions that I haven't been able to answer. Those are great examples of things you might want to pursue on your own. I know it's crazy, but I actually don't know everything in astronomy, and I'm actually very curious to see what you all are excited about. In the past, people have done little research projects on modified gravity, for instance, as a way of getting around the need for dark matter, and then sort of presented some of the observational conflicts with some of the sort of current theories of modified gravity, sort of talked about what might happen in the future. People have done art projects where somebody simulated, or they made real in 3 dimensions what 4-dimensional curved space-time might look like around a black hole. That was pretty crazy. People have done songs. People have written JavaScript code to calculate the luminosity distance to a given source as a function of redshift. It's kind of up to you. Obviously, it should be on a topic near and dear to our heart in 7B, and you haven't seen a lot of cosmology yet. That'll be coming up essentially starting next week. So you may get interested in some of those aspects. What we would ask you to do is, as you think about potential projects to do, you just ask me and or the GSIs about our thoughts on that to see whether perhaps the scope might be too large, or maybe it's too small, or we don't think it's appropriate. And once you get the okay, then you can go off and do your thing. Essentially 3 to 4 pages if you're doing something written, or 3 to 5 pages if you're doing something written. And then if you're not doing something written, you're doing something on the web or something, a 1-page summary. Okay, right, so everyone who turns in a extra credit project that's, you know, well thought out, well done, etc., gets 2 points in total on your final score. And I should say that we will calculate the letter grades of this class, not including the extra credit. So if you're on some sort of, you know, transition zone between like a B+ and an A-, and those 2 points put you over, then you get an A-. But it won't skew the initial distribution of letter grades. And the best one gets more points. Sections will be as normal starting tomorrow. So we'll have one on Friday, we'll have one on Monday that relate back to the material that we've been doing this week. Colloquium today is by the same speaker as yesterday, the Sackler lecturer, Andrea Getz, and she'll be going into more detail. That was a popular lecture, popular level lecture in the sense that she wasn't using lots of equations and things, just explaining to lay people what it is that she does. So today you'll hear some more of the details. I think a couple of you guys went, right? What'd you think? Interesting? I thought the questions after were very good. There were a bunch of people I've never seen before asking very hard questions. Yeah, it was an interesting lecture. Any questions on logistics? What's that? Oh, it's at 4, yeah, and that's in number 1 LeConte. So last time we did fundamental relations of galaxies. This is relating observable properties, say the brightness, to other properties, say the size. And you can do these in physical quantities like luminosity and physical radius, say in kiloparsecs, or you can do this in apparent magnitude and size in angular units. And we talked about these relations, obviously, because it gives us some insight into the building blocks of galaxies, understanding that there's a relationship between the luminosity of stars and the total amount of dark matter. That's an important relationship. That comes primarily out of the Tully-Fisher relation. But we also saw that when we started talking about ellipticals. In terms of the properties of ellipticals that were interesting, the Faber-Jackson relation is the first fundamental one from the 80s, showing that the luminosity of an elliptical galaxy appears to go like sigma to the fourth. Can people remind me what sigma is? Velocity dispersion. What does that mean? It's not so much. That's sort of right. It's related to the motion of stars towards you and away from you. So there is a sort of Doppler component to it, but it's not usually measured in an absolute sense. What you wind up seeing is that there's a distribution of stars of certain velocities moving towards you and a distribution of stars moving away, and so that sigma winds up characterizing the width of that distribution. Yeah, it's a standard deviation of that velocity. And that's something that you can measure by taking a spectrum of an elliptical galaxy at some position. And what you see is that there's some projection of the motion of all the stars towards you and some projection away from you. We also saw surface brightness fluctuations was a way of making measurements, in particular to spiral galaxies, measurements of distance. And there we saw that given the fact that you have a surface brightness which is constant, regardless of what the distance is to that source. The thing that's not constant is the fluctuations of many little patches of the same surface brightness. There'll be some slightly brighter, some slightly fainter, and the farther away you go for a given fixed angular size on the sky, the less those fluctuations become. And that just has to do with Poisson statistics, that you have more stars in your box, and therefore the overall sort of fluctuations of the total numbers within boxes winds up going down proportionally. Right. Part of the Faber-Jackson relation, which is a fairly decent scatter about this line, is actually reduce that scatter by invoking the fundamental plane and saying that it's not just luminosity and velocity dispersion, it's also some sense of an effective radius. And when you combine all three of those parameters together, you get a very tight relation of elliptical galaxies of all different masses and all different velocity dispersions about this sort of projection of a plane. And the last thing that we ended with was this very strange relation, something I don't think I actually gave you how we symbolize this, but the relationship between the mass of the black hole at the center of an elliptical galaxy versus the velocity dispersion of that galaxy. And it's not just ellipticals, it's actually bulges, so S0s and even ordinary spirals. People have been able to find this relation. The Milky Way essentially falls on this relation, even though it's not elliptical. It does have a velocity dispersion of its bulge, and there's a very tight relationship between the mass of the black hole at the center and the overall velocity dispersion. Even though an individual black hole only has, as you saw very, I think nicely for those that went to the talk yesterday, only has a sphere of influence at sort of the few parsec level. Beyond a few parsecs, all the motions of all the stars don't really care about the fact there's a black hole at the center with 10 to the 6 or 10 to the 7, 10 to the 8 solar masses. That's dictated, the motions of the stars are dictated by the dark matter content. So this is very surprising. We don't have a great sense of why these two things are intimately related, but they are. All right, were there any questions about what we did last time? Right, okay. So now we've got a sense of how galaxies are like other galaxies of the same type in physical units, right? We have ways of relating the properties of different galaxies together on plots. So we have sort of an overall sense of how galaxies might be distributed in mass, or how they might be distributed in luminosity. But what we don't have is a sense of how galaxies are distributed in space. Are there more ellipticals? Are there more spirals? Are there more dwarf galaxies? I think some of you have an intuition about this already, but I thought the way we would talk about the distribution of galaxies of different types in space is start off with a sort of overview of what's called the local group of galaxies around the Milky Way. This is a depiction from 2005 from a textbook of the distribution of basically everything we knew that were gravitationally bound systems that were essentially larger mass than a globular cluster and weren't obvious constituents of individual galaxies. That is, galaxies in their own right, or if you like, island universes. Here's the Milky Way, and here's sort of the very local universe around the Milky Way. There's some very famous satellite galaxies, and we've talked at great length about the Small Magellanic Cloud and the Large Magellanic Cloud. And then there are these other so-called dwarf galaxies or dwarf irregular galaxies in this local group. We're all in sort of a gravitational dance around each other, as you saw in the opening movie. But the dominant source of the gravitational potential is from the Milky Way and from Andromeda. And the way that you might think about this is you have two very large dark matter halos, and at the center of them are Andromeda M31 and the Milky Way, respectively. And all of these little dwarf galaxies are essentially orbiting around. We know that the Small Magellanic Cloud and Large Magellanic Cloud are sort of on a collision course with the Milky Way eventually. They will be, as we'll see, I think towards the end of class, tidally stretched and ripped apart, and they'll just become part, their stars and their gas will just become part of the Milky Way eventually. The distance between Andromeda and the Milky Way, surprisingly, isn't known incredibly precisely, but the current number is something like 770 kiloparsecs. So a good number to keep in the back of your head when we talk about local groups of galaxies is something like a megaparsec. This is not what would be called a large cluster of galaxies. We'll talk about large clusters of galaxies on Tuesday, but it's a reasonably sized. Having two large spirals is a pretty nice thing because we can study another spiral galaxy a lot like our own, and we're not obviously embedded in Andromeda. Let's see, what else is there to say? Well, okay, so the other spiral is M33. That's basically a satellite of Andromeda. And there are about 45 galaxies in total in our local group. Any bound group of galaxies, which is sort of nomenclature, might be called a galaxy cluster. We don't think of our local group as a rich galaxy cluster. What's interesting is that even though we've learned a lot about the universe as a whole over the last century or so, we don't know a whole lot about our local group of galaxies. And in particular, I'll turn off the light here. People are finding new satellites of the Milky Way all the time within the local group. This is a very faint, low surface brightness galaxy. So this is how you might visualize surface brightness. Draw a box here, draw a box up there. Obviously, the surface brightness in here is much smaller than the surface brightness up there. It was thought for a while, this little blobby thing, or nebulosity, was believed to be associated with that galaxy up there, which is actually quite far away, something like 50 megaparsecs. But then, I think only a few years ago, maybe 2-3 years ago, people started taking spectra of this thing here, and they wound up realizing that it's actually got a negative velocity. It's actually quite nearby us, and probably falling into the Milky Way. So this was the discovery, after this thing had been known for 23 years, a discovery of essentially a new galaxy within the local group. And why is it that it's hard to find? Well, it's low surface brightness. It's not obvious what its distance is just by looking at it, right? Basically, we haven't had very good all-sky surveys to be able to see these very low surface brightness galaxies. There may be other galaxies on the other side of the Milky Way that are faint that we can't actually see at all because it's hidden by dust from the dust lanes within our own galaxy. So people have been really making an industry out of finding new dwarf galaxies And there was basically an announcement of a discovery of 8 new dwarf galaxies in 2007. People who analyzed lots of digital images from what's called the Sloan Digital Sky Survey. And it might be hard to see, but that's actually a cluster of stars which are gravitationally bound. You can actually measure a velocity dispersion, so you can figure out the total mass of that system. And it's quite nearby. So this is a pretty remarkable thing. Here's a summary of some of these new ultra-faint dwarf galaxies, as they're now called. They have these funny names based on which constellation they appear to be in. Obviously, these are ones that are behind. And look at their masses. Just a couple times 10 to the 6. A few million solar masses of stuff. They tend to be very, very dark matter dominated. Look at the mass to light ratios. Right, all this stuff is coming together. You can now actually look at these tables and know what these things mean. What does this mean? Metallicity. Yeah, low metallicity, and they're probably very old. So these things have been around for a while. They've basically formed all the stars they're going to form. Metallicity is 1/100th the times the metallicity of the sun. Very, very small metallicities. And you can see the dispersions in those metallicities are also quite small. This is a remarkable thing. The fact that the mass to light ratio in these things is orders hundreds, if not thousands, means that these little satellites are completely dark matter dominated. Remember, we said for spirals, this number was something like 4. For ellipticals, this number was something like 50, maybe up to 100. And these things, for whatever reason, are incredibly dark matter dominated. Again, how would we know what this m divided by L is? If I just gave you this image of the sky and said, there's a new dwarf galaxy, tell me what the mass to light ratio is. How would somebody construct an observational program for me to tell me how I would figure out the mass to light ratio?
Estimate how many stars there are.
Okay, or we could just count them. Yeah. Okay, so then what does that do?
Well, if you know what kind of star it is, you can find like the mass of the, and then you can get the light just by taking stuff.
Right, so we can get the luminosity by just essentially integrating all the light that we get from all of those stars. And if we know the distance, then we can figure that out. But is that how we get mass? Yes, that's right. So what does this mean? That if I just thought that these little baskets of stars had no dark matter in them, would they be moving faster or slower relative to each other? What would their velocity dispersion be relative to what I actually measured? Would it be less or more? Less, that's right. Because they actually have fairly large velocity dispersions, it means there's a lot of missing mass that's accounting for this large motion, right? And that's how you wind up getting the mass, is through velocity dispersions. You get the luminosity through essentially counting stars and integrating the light of those stars. And it's the ratio of those two that give us this number. It's fairly remarkable. Okay, so that's our local group of galaxies. And what should be clear is that it's, again, in some sense, very hard to study the Milky Way because we're embedded in it. It's actually hard to study the local group of galaxies because we don't know where to look on the sky for the next dwarf galaxy, which might be associated with the Milky Way. And in particular, there may be a whole bunch of dwarf galaxies on the other side of the Milky Way that we may actually never see. So studying other clusters of galaxies is not a bad idea. By the way, this is a paper that came out just recently by the same person that did the Tully-Fisher relation. What you see is a cumulative distribution of the total numbers of galaxies in a bunch of different clusters. And what's nice about studying clusters is that you can focus all your attention on just a small part of the sky. So even though each one of these galaxies may appear fainter than one that's really nearby, you can use much larger telescopes to study and find those very faint galaxies. So you can go very far down. Does anyone remember what the absolute magnitude is of the Milky Way, thereabouts? In R. It's about here. It's somewhere between minus 19 and minus 20. That's, again, a hard thing to figure out. Andromeda is about here. So these are very bright spirals and ellipticals. And we haven't told you what the different types are here. So there's not a lot of them, right? And then as you go farther down, what's called the luminosity function, farther and farther down, a factor of 100 fainter would be here, right? 5 magnitudes. Another factor of 100 would be down here. So this is 10,000 times fainter than a typical large spiral. So you can go 10,000 times fainter, and you're still counting galaxies. You go down so far that you're starting to reach the typical brightness of some of the brightest individual stars. O stars and B stars might be around here. It's pretty remarkable, right? And what you see is that some of these things have a whole lot, some have a whole less. But a generic property is that for every few spiral galaxies or elliptical galaxies that you have up here on the bright end, there's vastly many more dwarf galaxies. That's the thing to take away. This is the cumulative distribution. There's another distribution that actually sort of captures the shape of this, not in a cumulative sense, and that's called the Schechter luminosity function. Look on the left first, and then I'll explain what's happening on the right. Okay, so the 1976 paper that fit the distribution of the brightness of galaxies in a cluster, the cluster's name was Abel, is one of the Abel clusters. Actually, it was multiple Abel clusters. Just essentially counted the total numbers of galaxies in some small magnitude range. So you count the total number here, and you just make these little bins. And there's this line that's drawn through this. I'll give you the functional form of that in a second. Again, this captures our sense of things. For the very brightest sources, there's vanishingly few of them, right, at the sort of Milky Way level, and then brighter. And then you have vastly many more of the dwarf galaxies. This is characterized, this shape, by this alpha, something called M star. And what's interesting, so Schechter sort of said this was, and this is kind of what he looks like. He's a professor at MIT. Said that this might be actually universal, that the distribution of galaxies of different sizes may actually fall along this. It's a power law up there. It's an exponential down there. It's characterized by a certain number right here, called the knee of the luminosity function. And the whole idea here is that we don't actually know the detailed physics of why, when you get a conglomeration of galaxies, that it actually has this functional form. But it's got that form because that's what you need to do to get rid of the details, the physical details. This is sort of astronomy nerd humor. All right, so let's look at the functional form of that. And then we'll talk about galaxy formation and how galaxies came to be. All right, so the distribution of galaxies in space is an interesting one. There's something called phi of L dl, which is just the total number of galaxies per, say, megaparsec cubed per unit L, per unit luminosity. So this is more or less just a density, but it's a density within a small, narrow range of L. This, the Schechter luminosity function, is parameterized with L to the alpha, e to the minus L, divided by something called L star dl. Typically, alpha is something like -1, and I'll tell you what L star means in just a second. Well, the total number, L is sort of like 10 to the 11 solar masses, or solar luminosities, L star. And if you make a plot of this functional form right here for the parameters I just gave you, it kind of looks like this. with L increasing to the right, and this sort of knee of this so-called luminosity function is L star. Cubed, thank you. I think I said cubed, but I wrote squared. Thank you. Yeah, it's a sort of volumetric total number. This number, if I integrate it from, say, 0.5 L star to 2 L star, so kind of around this area right here, that number turns out to be about 10 to the minus 2 per megaparsec cubed. So in every sort of 100 megaparsec cubed volume is where I would find one big spiral or one big elliptical on average. That's on average. Now, this isn't exactly true because galaxies are clustered. In fact, a good thing to remember is that the best place to find a galaxy in the universe is near another galaxy. Galaxies are not evenly distributed over the whole sky. If you find one big spiral, you have a much higher probability of having another big spiral nearby. But on average, this should give you a typical number for the space density of big galaxies. Because we've been doing things in terms of magnitudes, we can also write this luminosity function in terms of absolute magnitude, phi of m dm, and that goes like essentially taking minus 2.5 times the log of this number, 10 to the minus 0.4 alpha plus 1 times m, e to the minus 0.4 m minus m star dm, and now m star is the same magnitude of a source that has luminosity L star, and this number is typically minus 20 to minus 21. Depends on your magnitude system, depends on the specific galaxy cluster that you're looking at, and actually when you're looking in the age of the universe. That's for all galaxies, but if I take the log of phi of L for different types of galaxies, I can get a good sense now, and I'll just sort of depict what this might look like. In a typical population, in a typical cluster, I'll have magnitude increasing this way, so it's getting fainter to the right, minus 22, minus 20, minus 18, minus 16, etc. This is ellipticals. Let me do spirals. Something like that. And then we'll do irregulars and dwarf ellipticals, as they're called. Basically faint stuff. This is obviously not an accurate depiction, but there's a couple things that I wanted to highlight here, because this is supposed to be illustrative, is that the brightest galaxies in any given cluster are going to be ellipticals. Now, we don't have a large elliptical galaxy in the local group. Again, this is one of the reasons why we don't think of ourselves as a large, rich cluster. Ellipticals are the brightest objects in clusters. Then spirals are more numerous, it's sort of the minus 21 to, say, minus 16th level, and those numbers are dropping off very quickly as you go to fainter levels. And then sort of bringing up the whole thing are these dwarf ellipticals and irregulars. So that should give you a sense, if I just sort of had a sort of certain large volume that encapsulated all these different types, what that sort of distribution might be in space. One of the things that's important to recognize is that if I integrate phi of L dl from 0 luminosity up to infinite luminosity, it depends on what this value of alpha is. And if alpha is anything larger than -2, then that integral winds up diverging, which winds up telling us that our prescription for a luminosity function of galaxies, this prescription right here, has got to be wrong. Yeah?
Is that still phi L on the y-axis?
This is log of L. Log of phi L.
Phi m a second ago.
We could do it that way too, because there's an m and L relation just by a 0 point, right? It's just kind of easier to depict this rather than me saying, 10 to the 11 solar mass, 10 to the 11 solar luminosities, 10 to the 9, 10 to the 6. You could, of course, just write those down here too, but that's just a little bit easier because we've been thinking in terms of magnitudes. Right. If this is -1, which it appears to be observationally, down to very faint levels, then we have a serious problem. And what's the way that we get around this problem? You don't even do the integral. Yeah, essentially right. I mean, what happens is at somewhere at very faint levels, our concept of a galaxy winds up going away, right? And then we're left with basically stars. So you obviously have a finite number of galaxies in the universe, but we don't really know, even for the most and the best studied galaxy systems, we don't know where this turnover actually occurs. And what the physics is that sort of gives us that turnover. That's an interesting thing that I think people are going to be working on for the next several years. Yeah?
How is this mass calculated?
It's not a mass. That's magnitude.
Oh,
yeah.
Okay, I thought we were going to mass.
Okay, any questions about the space distribution of galaxies? Yes, Josh. Oh, e to the minus 0.4 times the quantity m minus m star. The minus 0.4 is just 1 over 2.5. Okay, so let's talk about galaxy formation. Galaxy formation obviously has to be discussed in the context of an evolving universe. The age of the universe over which these galaxies can form, something like 14 gigayears, 14 times 10 to the 9 years. And the current best estimate is 13.75 plus or minus 0.13 gigayears. So a little less than 14 billion years to evolve. How is it that galaxies came to be if one of the basic tenets of cosmology, as we'll see, is that the universe is homogeneous, especially at early times. It's incredibly homogeneous. That is, in this little parcel, and this little parcel, and this little parcel, everything is the same. It's the same density, it's the same temperature, it's the same constituents. How do you go from almost complete uniformity to these incredibly evolved structures that we have around us today? And the answer is that dark matter plays a very important role in bringing everything together. Now, if you had a perfectly homogeneous universe, then even if you had lots of dark matter, you wouldn't be able to create these very massive structures, which is basically taking a large amount of mass and some volume and compressing it down to a much smaller scale. That's how we get these large, high-density structures. But starting off with this almost completely homogeneous universe and getting to where we are today is a big part of cosmology and is an even bigger part of understanding galaxy formation. So we can understand the sort of transition from complete homogeneity to inhomogeneities that give rise to these structures by looking at simulations of the very early universe. Did you have a question, Virgil?
Where you said that well, I thought that it was due to like density fluctuations in the universe that created large scale structures.
It is.
Oh, never mind. I thought you said that.
It's incredibly homogeneous, but not 100% homogeneous. This is a depiction about half a billion years after the Big Bang. No, even less than that. 10 million years after the, sorry, start over. 100 million years after the Big Bang, and a huge volume of space. On one side here, forget about what this H means here. On one side, this is 500 megaparsecs. So remember, the size of the local group is about one megaparsec. So the local group of the Andromeda and the Milky Way would sort of comprise a tiny little pixel right here. This shows you what the inhomogeneities of the universe look like. It looks almost completely uniform, but you see a couple of fluctuations above and below. The density fluctuations here are something like 1 part in 10 to the minus 4. So very, very homogeneous, but not exactly homogeneous. Now, the nice thing about gravity is that once you have a small extra amount of mass in one little place, that is, the density in one place is a little bit higher than the density is in another place, all the mass around there wants to flow into that. So you can play this as a movie going forward in time. And what you see is that over time, and this is now going from, what did I say, 100 million years up to about 1.5 billion years. What you see over time is that these inhomogeneities become larger and larger. Turn off the light so we can see this a little better. The H is a parameterization of the Hubble constant because the universe is expanding as we go forward in time. As we go backward in time, it's effectively getting smaller. So we know how much it's changing, and the Hubble constant sort of parameterizes that change. So by using this little h, it allows us to look at the same volume, the same sort of parcel of space, even though the volume may be expanding. All right, one more time, and then we'll talk about the properties of what we see. What you notice, these little hot spots here are regions where you create galaxy clusters. And in this entire simulation here, by the way, all we're looking at is dark matter, right? It's kind of been color-coded to make it look like it's stars, but it's basically only here and maybe here and a few other places do the densities get high enough that you get large numbers of galaxies and you wind up creating galaxy clusters. So galaxy clusters, as you should see right away, are fairly rare in the universe. That's one thing. You also should see that mass likes to assemble itself under just the presence of gravity with lots of dark matter in these sort of long so-called filaments. The way people sometimes look at this is they call it a cosmic web, or I think of it more as sort of some sort of bubble, bunch of bubble structures. And in fact, what people say when they look at these black spots here, that these are called cosmic voids, where you don't have any appreciable amount of dark matter, and very few galaxies reside in those voids. So in the context of a universe which is expanding, which we're sort of taking out by this little h here, even though the universe is expanding, we get these nonlinear structures, we wind up getting this collapse. So when we think about individual galaxy formation, we should be thinking about some large structures, say large clouds, which wind up collapsing under their own gravity and wind up forming, say, proto-galaxies, which themselves over time, over billions of years, can wind up assembling to create larger and larger galaxies. Oops. All right, so galaxy formation has a long time to go if it wants to. Galaxy formation starts, however, when the universe was much younger. it was younger, it was more dense, and it was significantly more hotter. There are significantly hotter. There are really two main theories for how we wind up getting galaxies as big and as structured as the Milky Way. And what I'll do is describe just sort of in broad terms what those theories are now, and then we'll go through some of the physics of galaxy assembly and galaxy collapse. The first theory for galaxy formation is the so-called Eggen-Linden-Bell sandwich theory. Uh, 1962. I didn't write it down. I think it's 1962. It might be 1963. And the idea here is that you have a proto-galaxy essentially a large cloud. That collapses. Typical numbers that you get from just sort of playing these cosmological movies forward is that you might start from an initial radius of this cloud of something like 50 kiloparsecs. If you're looking at the Milky Way, you might look at a cloud of mass, something like 6 times 10 to the 11 solar masses. And so the density, which is just going to be the mass divided by 4 pi, our initial in physical units is about 10 to the minus 22 kilograms per meter cubed. If this cloud just sort of decides to collapse, how long does it take to collapse? No, we'll assume no pressure support. It just says, oh, I just reached some critical density, or I just reached some critical size or critical mass, and I'm going to collapse.
Time that it takes to fall under the gravitational influence.
Yeah, free fall time. That's a natural time scale in trying to understand how long it would take to get this very large cloud to collapse to a much smaller size. Now, if you're doing this in detail, you might do the integral as r goes from 50 kiloparsecs, not down to a small number, but down to something like 10 kiloparsecs, some typical size of where all the gas and the stars are in general in the Milky Way. Does anyone remember what the functional form is of the free fall time? What does it depend upon? Depends on mass, but it's actually even easier than that. Just density, right? If I have a large amount of mass, and the radius is very large, it could have the same free fall time as something with not a lot of mass and where the radius is small. The only thing that it matters is the initial density. And you can put in all the numbers for a spherical cloud, and you get 3 pi divided by 32, 1 over g rho initial to the 1/2 power. This is actually a very helpful thing to remember, is that when you're talking about timescales of things collapsing, you saw this if you took 7a in the context of star formation. The free fall time is an important number. It goes like 1 over rho squared, to the 1/2 power, excuse me. If you put in these numbers, you wind up getting something like 200 million years. What's the attractive thing of thinking about this sort of collapse of a very big cloud to just form the Milky Way? What's attractive about that is that if you think about the orbits of stars as they're forming, because as you're collapsing, 200 million years is a lot longer than the life cycle of a very massive star. So as this thing is falling down, you're making stars, right? As you wind up increasing the density, there'll be slight inhomogeneities. This won't be purely homogeneous across the whole thing. You'll get these little pockets of extra density. You'll make stars all over, and then those stars are going to wind up falling through. This is a great way to think about making a halo of stars, right? Because the orbits of these things as they fall in just going to wind up being the initial orbits of the initial parcels of gas. Those stars that stay associated with gas, and in fact the gas itself that doesn't make stars initially, are going to fall in. And if there's any angular momentum to this initial cloud, then you imagine the whole thing would wind up rotating. And this whole idea of getting this pancake of gas, which winds up forming newer stars, is quite natural in this. This is actually a reasonable idea for how you make a very big Milky Way. How you make very small ones, it's a little bit harder to understand that. How come they don't also have these spiral structures? But if we're just thinking about the Milky Way and the Milky Way formation, this isn't a bad idea. However, it's not right. Or at least it's not right in some very important aspects of it. One of the things that's not right about is that, although this seems like a long time, 200 million years, what is it that we know about the distribution of stars within the Milky Way in age? Or think about it in terms of metallicity.
The ones on the disk are the youngest.
The ones on the disk are young, and they could be quite, there's star formation happening right now, right? Some of the stars in the halo or in the bulge are quite old. And they could be as old as, almost the age of the universe. In fact, some people have been looking at this to try to find some of the oldest stars. Metallicity is 10 to the minus 4 solar. One of the problems is that this theory, which is sometimes called ELS, because it's hard to say, Egan-Linden-Bell-Sandage theory, and it's wrong, is that the age spread under this theory should be much less than observed. And the other problem, which is a little bit more of a subtle one, is that the velocity, or actually the angular momentum, in the inner disk should be much larger than it actually is. And there's a couple other more subtle problems with this. I don't really want you to know the details of why this might be wrong. I just want you to know that the idea of taking a very large cloud, having it collapse, and having it somehow magically form into the Milky Way doesn't appear to be right. If this isn't right, and again, this is sort of the big thing, right? It's that the spread of ages of stars within the Milky Way is kind of all over the map. Some of the stars look like they're as old as the universe. Some are being formed right now. Is that when we look in detail at these different populations, as we did when we looked at the Milky Way, we look at their ages, we look at their metallicities, instead what it looks like is that you have some sort of large population of old stars in the halo, and those have specific orbits. Then you have all these new stars, and then there's all the stuff in between. It kind of looks like you had building blocks of different galaxies that formed stars, formed a big burst of stars at some age, and those stars all sort of moved around with each other for a while and eventually wound up accreting onto a more massive system, the proto-Milky Way. And we see this in action right now. We are in the process of accreting the small Magellanic Cloud and the large Magellanic Cloud onto the Milky Way, and there are a lot of young stars being formed in both of these regular galaxies. And so what's interesting about this is that, if you looked at the Milky Way in 1 billion years from now, or whatever, 2 billion years from now, after we've accreted the Magellanic Clouds, all of a sudden we have this new infusion of gas, we have this new infusion of young stars, and they would have a different metallicity, different properties, etc., than the stars that are already in the Milky Way. So the Milky Way is a conglomeration of heterogeneous blobs of star formation that have happened at different times at different metallicities. And so that's why we see it as we see it. The theory, hold on one sec. So really the way that we think about galaxy formation is that mass is assembled in smaller pieces that fall into each other to make larger structures. This is sometimes called the hierarchical merger model. Or bottom-up assembly. The idea that you take these little pieces of galaxy fragments, you merge some of them together to form a larger fragment, and these things all fall down onto the larger one. If that's the case, what's the origin, or what could be the origin of the angular momentum associated with the disk of the Milky Way? Yeah. So you've got these little pieces, they're all sort of dancing around each other, and there's an angular momentum of, if I just draw a circle around these two, there's an overall angular momentum associated with the orbit of that. There's an overall angular momentum associated with the orbits of those, right? And then the overall final angular momentum is just the sum of the angular momentum over the whole system, as I started off with. At some level, this isn't so different than this other picture, in the sense that we do have a big parcel of gas that instead of all collapsing at once, it just fragments, and then it winds up coming together. So it's how you sort of play the movie forward in time that winds up dictating how you wind up getting these very large spreads in ages. And the important thing is that the star formation history in this little parcel may be very different than this little parcel, right? Because the star formation history is going to depend upon its early interactions with other little blobs. So let me show you a couple depictions of these basic building blocks. We'll see a couple movies of mergers and galaxy assembly using these smaller building blocks. And then we'll go into some of the physics of this collapse and point out that the freefall time is an important one, but there's another important time called the cooling time. When we look back, I think I've shown you this slide before, when we look back in time, which we can do with our telescopes, because we look back very far away, and when we look at something that's far away because of the finite travel speed of light, we're looking at those galaxies as they were when the universe was younger than it is now, and we're looking at basically old light. What we see when we go farther back in time is we see more and more of these little building blocks. And many of these building blocks appear to be quite blue, so they're forming stars very rapidly. But these are tiny sort of half kiloparsec blobs. And there's many more of them as we go farther back in time. So where did they go if we play the movie forward in time? Well, they wind up actually merging with each other and forming larger and larger structures. And some of the most dramatic things that we can see kind of happening right now are when you get a bunch of these little building blocks after they've merged, have formed a large structure, and then you get another large structure hitting that, right? So mergers of spirals, large spirals, are quite possible. And I said that when I showed you this in the context of irregular galaxies, that this was sort of a poster child for the merger of two large spirals. This was probably a spiral, and this other thing sort of zipped right through it. It changed the potential of both of them, and you wind up getting this huge shock wave which propagates outward, creating a lot of star formation as this ring propagates outward, the shock wave. So here's a simulation of this with a supercomputer. Each individual particle that you see there is about 1 million solar masses of just dark matter stuff. They're not that concentrated, but this was an early simulation about 10 years ago when it's harder to get lots of even more finely grained particles. But you see that the structures that are set up from this interaction look very, very similar to the ones that we actually see. So this isn't so much, again, the merger of two building blocks. It's sort of the merger of blocks that have already been assembled. In groups of galaxies, this is called the Hickston compact group. You see a number of galaxies, actually of different types, that are all in the process of this merger. Here's an edge-on spiral. Here are our dust lanes. Here, what looks like a reasonably sized elliptical galaxy. And up here, here's another spiral. Here's another spiral. All these things are actually in the process of merging together. So this is in the very late stages after these building blocks have assembled. Here's something called Seyfert's sextet, because there are 6 galaxies which appear to be merging into each other. All of these are at about the same redshift. That one is at a different redshift or a different distance from us. We don't know if it's actually physically associated. And people have tried to simulate this system to see what will happen. The important thing is when we think now not building up from these blue galaxies, the little blue building block galaxies, but to something larger into spirals, it's what happens after you merge spirals that's very interesting. And we think that's how you wind up getting large ellipticals. So here's this. You guys are bummed that I don't have music. Whoa. Notice how the spiral structures are basically disappearing through this. Okay, yeah. I didn't do that. All right. So let's look in detail now at some of the physics of galaxy collapse and assembly. And indeed, the freefall timescale is an important one. But to get freefall, you have to have lost your pressure support. Because, as I said, especially in the early universe, this gas is hot. And so there'll be an internal source of support until we wind up getting rid of the heat associated with the motion of the individual particles within that gas. So it does the Eggen-Lindebelle-Sandage theory, ELS, doesn't work in detail for the Milky Way, but the idea of collapse is indeed correct. It's just sort of the ordering of the collapse at different sizes that's important. The so-called dynamical timescale, well, the freefall timescale, we said goes like 1 over rho to the 1/2 power. And for the parameters that I gave you, this is something like 200 megayears. So indeed, you could take a small parcel, which has a density similar to this, could have a mass much less. But these are the typical densities that you wind up seeing in the early universe. That typical density will wind up having a free fall timescale associated with it of 200 million years. So that might be a typical number you might think of, not just for large clouds to collapse, which is certainly possible, but even small fragments of clouds to collapse if they have a density like the numbers that I gave you before. we have this internal pressure that's going to halt us from collapse. And so we know what that means, sort of cutting to the chase. There is a Jeans mass associated with a cloud which is on the verge of collapsing. And that Jeans mass goes like 5 kT g mu mh. You've seen all this before. Just get it back down. 3 divided by 4 pi initial density to the 1/2 power. And the mass must be larger than mj, Jeans mass, to collapse. So for a fixed mass of a cloud, which is on the verge of collapse, what's the easiest way in which I can do this? This is basically a statement about losing pressure support. When the temperature decreases. Okay, so if I have some temperature associated with a cloud of some mass, and it's being held up because it's got an internal pressure that's keeping it up, at some point, if the temperature goes down below some critical number, all of a sudden the mass of the cloud is equal to Jeans mass, and now I can fall. And you won't fall exactly on the free fall time scale, but this is a reasonable number. What you actually need to do, because at every moment you're going to reevaluate what the free fall time scale is and what the Jeans mass is. As you wind up collapsing, of course, now your temperature is going to wind up going up. And then you have a new free fall time scale because your density has changed. What you need to think about is a time scale associated with the removal of a large amount of the heat, the kinetic energy associated with the motion of the gas itself. So we want to know what a cooling time scale is. T cooling is the time it takes to remove the kinetic energy associated with the gas cloud. Well, let's think about for a second what it is when we think about a temperature of a gas cloud. We'll think about the kinetic energy of that gas cloud, and then we'll come up with a sort of way of thinking about T cooling and how we might figure out what that cooling time scale actually is. So if I have a typical velocity of a particle whose mass is something like m, what would be the total mass of, or total kinetic energy of my gas cloud? Yeah, 1/2 mv squared times the total number of particles. If I want to associate that with temperature, yep, 3/2 is a chemical temperature, N kT, same number right here. The ends will wind up canceling. We want to do this in aggregate, and obviously every particle won't have exactly the same mass. Every particle won't have exactly the same velocity. So if we're being careful about this, we would say 1/2 mu mh, so this is the mean molecular mass of every particle, times some average velocity squared, and we'll get rid of the n's, is equal to 3/2 kT. This T, sometimes called T virial, then is just mu mh. What is this quantity here in terms of something I can observe if I'm looking at this gas cloud collapse? Velocity dispersion divided by 3k. So that's this temperature that we're talking about, right? It's a temperature which is related to the velocity, right? That's the v squared right there. All right, let's look at loss of energy, loss of kinetic energy. How might we lose kinetic energy? How might we remove heat from this system? What's that?
Radiation.
Yeah. What kind of radiation? What's that? Line radiation? What? Light radiation. Yes. Yeah, we could have thermal. We could have bremsstrahlung. What else? I already said it. Line cooling. That's right. So depending upon the temperature of the gas, there's going to be different regimes where we can remove the heat. And it's certainly beyond the scope of us going into the details of what this cooling curve might look like. But it's usually, it looks something like this as a function of temperature in Kelvin. This is log. So this is 10 to the 7, 10 to the 6, 10 to the 5, 10 to the 4. And I'll give you the symbol for this. It's a capital lambda in units of watts meter cubed. I'll tell you what these different regimes are in a second, but let me just say that the energy loss per unit time, per unit volume, per meter cubed, let's say, is what we call the rate of cooling. This is going to go like n squared times this quantity right here. This is usually called beta of T. Well, first of all, let's look at the units for a second, then we'll try to explain why this is a great way to think about how cooling happens. The units, energy loss, the Y, energy loss per unit time per meter cubed is basically a volumetric energy loss rate, right? It's a luminosity per volume. If the units of this are watts meter cubed, if I multiply by 1n, this is the number density of particles, then I have watts. If I multiply by another n, then I have watts per meter cubed, which is this. Okay, so the units work out. Why am I plotting this with it? Why do I need to have an n squared and not just an n? Why is the rate of energy loss dependent upon how much stuff I have squared? I'll give you a hint. This is bremsstrahlung. I don't know why I can spell that and not spell energy. Yeah, that's right. It requires. Remember when we talked about the Stromgren sphere, we talked about the rate of recombinations, right? We talked about, well, you need to get an electron and a proton near each other for you to even have a recombination. That's, one type of particle, another type of particle. The densities, the number densities are going to be the same if you started off with a neutral gas. Same thing here. To get bremsstrahlung, what is that? It's a proton, and then an electron passes by. It winds up curving. It's accelerating. It produces light. Light is heat. And that's how you do this. And actually, the higher the temperature, the more bremsstrahlung radiation you end up getting. So you need n squared because you're talking about particle-particle interaction. This is called helium recombination. This is hydrogen recombination. So there's a sweet spot when you've got enough particles around of electrons and protons at some sort of temperature around 10 to the 4 Kelvin that you get lots of recombination, and this is a way of essentially removing heat from the system. You remove chemical heat because you take an electron and proton, you turn it into one particle, so n goes down by a factor of 2. But you also take the kinetic energy of each individual free electron, and you wind up binding it up into the binding energy of now a neutral hydrogen atom. So there are these different regimes in an overall temperature of a gas cloud where you get different efficiencies for different types of cooling. In this low energy regime, you get line cooling. In the high energy regime, you get different kinds of cooling like Bremsstrahlung. And thermal is it's called thermal Bremsstrahlung. It's basically the same thing. At very low temperatures, I guess, like at the few Kelvin level or even tens of Kelvin level, you might be able to get sort of a thermal blackbody emission just because the overall particles might be emitting like blackbody. Okay. Now, let's figure out what this T cooling actually is. This quantity, BT, which is watts per meter cubed, times the volume, times the time, is units of what? Energy, right? And we'll just set this equal to 3/2 nkt. We'll call time T cooling. Volume you can put in in a density, and there's basically going to be a volume number here. This is going to be V. Let's do it. V T cool, 3/2 nk T vir. Put the V onto the other side. And what do we have? Not big N, but little n, kT vir. Substitute back in for what we have up here for beta, and we wind up getting T cooling of 3/2 kT virial divided by N of lambda T. That's our cooling time scale. So the criteria for collapse of a cloud is that the time it takes to cool is going to be more or less than the free fall time. Less. If I can cool rapidly, given the parameters that that I start with, then I'm capable of collapsing. Okay, this is the criteria for collapse. So we can put in the numbers where we set T cool equal to the free fall time scale. I don't know if I saved it right here. And keeping everything around, we wind up showing that the maximum mass of a collapsing cloud is just going to be this lambda squared divided by g cubed mu to the 4th mh divided by r of the initial cloud. There's algebra where you basically go here to here. And if you set these two things equal to each other and you have a mass of the cloud, you have a radius of the cloud, you wind up getting this quantity right here. So large cooling, this should now be intuitive, means that you can have a larger collapsed cloud. Larger radius means that you have to have a smaller mass. So putting in some numbers for what we might expect in the early universe, where we set R of 60 kiloparsecs as we had before, and a typical cooling number of lambda of T of something like 10 to the minus 37 watts meter cubed, we wind up getting a maximum mass of a collapsing cloud of 7 times 10 to the 12 solar masses. And what's actually interesting about this is, given this number here, and given the cooling time scale is going to wind up being, we can put it back in here, we can wind up figuring out what the temperature is. The virial temperature of this is something like 7 times 10 to the 6 Kelvin. So this is kind of the biggest type of cloud that we might expect that could collapse in the early universe. And we can look at where this sits in the cooling curve, and it's actually not able to cool very easily. There are other temperatures and other sort of times in the history of the universe where if there was a collapse, it might be easier to proceed, or we might get different masses. So what should be hopefully starting to emerge here is that depending upon the temperature of the cloud and the sort of overall density enhancement and how you actually get fragmentation in the early universe to different sizes of clouds and different densities of clouds, depending on all that stuff, we wind up getting a full spectrum of clouds that collapse in their total masses. And the time when they decide to collapse in the history of the universe depends upon the temperature of the universe at that time and that cloud's ability to get rid of heat around that time. So it's incredibly complicated, but it should also be clear then that you don't get all the galaxies forming of the same size, and you don't get them all forming at the same time. Yes?
This is saying, sorry, just to be clear, this is saying that we can't have a larger mass than that in order to classify a cloud?
That's right. So for a given fixed size of a cloud of some radius, and for a given cooling rate, there's a maximum size, maximum mass that I can wind up having that will wind up collapsing. So if I have a huge cloud and I have some fixed rate, if I have a very, very big cloud, and for a fixed density, I'm going to have some mass that I could wind up calculating, right? So you can sort of figure out in different regimes whether you're capable of making a cloud, or a collapsed cloud.
So I mean, between the Jeans mass and this maximum mass, we have given radius, and there's a couple of things for mass.
Right. So the Jeans mass is related to that in the sense that if I told you what the temperature of the cloud was, then I would have some mass, and if my cloud is more massive than that, then I'm going to collapse. Except for the fact that I collapse for a while, then I heat up, and then the question is, do I still keep on collapsing? The way in which you do this, and of course we're brushing under the rug a lot of sort of integrals of how you actually do, because of course as you change the temperature, you're going to move along this curve, right? But assuming that that number stays about fixed through the whole collapse process, what I want to know is how can I just remove essentially all the kinetic energy of my entire cloud, which is obviously totally unphysical. But it gives you a time scale for what this cooling is. So this isn't going to be wrong by more than a factor of a few. But this is what it has to be related to. Anthony, you have a question?
Yeah, the numbers for the universe. How do you know the cooling time number for 10 to the omega?
Lambda, you mean? Capital lambda?
Yeah.
So capital lambda is actually just due to the microphysics of the gas. If you tell me the temperature of the gas, you tell me the constituents of the gas. I haven't told you exactly the admixture of helium and hydrogen, which winds up setting what this value of mu is. That value of mu, by the way, for a hydrogen plus helium primordial gas is about 0.62. We'll start off on Tuesday with why that might be. The important thing here is that given the constituents of the gas, given the temperature, that's just a number I can calculate even in the laboratory, right? So that's just fixed, and then I just have to know what the overall size of the cloud that wants to collapse is. Oh, the 10 to the minus 37. I didn't give you units here, but it's about 10 to the units of 10 to the minus 37. right? And that's like 1, 2, 3. Yes?
Is this like kind of analogous to like a collapse like into a star? Like how come it turns into a galaxy and not a star?
It's the total mass that we're talking about, right?
So it's a different Jeans mass, or what is it?
Well, the temperatures are vastly different. That's for one, right? We're talking about, when we talk about star formation, we talk about temperatures of order 10 Kelvin.
Oh, okay. So it's just difference in temperature?
The physics is exactly the same of the collapse. That's not truly the case. There's some subtleties here in that the universe is expanding. So this galaxy is collapsing while the universe is expanding. So there's a couple of sort of small changes that you have to make in understanding this. But if I just said, let's now think about star formation, what I'd have to do is give you what this value is all the way down at 10 Kelvin. And then we could figure out if we can satisfy this criterion. Or that would give us the maximum mass of a star. Good. All right, we'll end with that. Next time we'll do galaxy interactions, and then we'll get into cosmology.